Okay, so we have so far in this semester we have seen um, the models in terms of transmission models and the reception models, which are applicable for advanced communication systems, including 5G and futuristic communication systems. And we have kind of tried to build a common unified mathematical formulations that apply to a wide variety of these models. Our first focus was on some estimation problem, and specifically there we looked at the frequency of arrival estimation problem, which actually is highly applicable to the wireless sensor networks and Internet of Things type of networks, where there may be a lot of unused spectrum, and a part of the spectrum may be occupied by narrowband transmitters, because a lot of these wireless sensors are transmitting narrowband signals. They do not have capability to transmit wideband signals. So that is just one scenario. There are other scenarios in which a wide spectral band is occupied by only a few narrowband signals. And then if I am a particular user of such a system, I may be allowed to transmit, provided that my transmission does not, in the frequency domain, sit on top of any existing transmission that is going on. And so in that context, this frequency of arrival becomes an important problem to solve, because if I can estimate the frequencies which are present in the signal that is being received over the air, then I know what are the locations which are absent of any signal, and I can make use of that unused spectral band. So spectrum sensing, frequency of arrival, these are highly relevant problems. We went over several papers written over just past few years on these problems. Then we saw that actually this FOA problem is highly analogous to DOA problem, direction of arrival estimation problem. And this DOA problem is also very much relevant in the context of the next generation systems, especially what are known as millimeter wave communication links. One of the characteristics of this wave is that the signal tends to become highly localized. It's almost like a point transmission, almost like as if you are shooting a laser from the transmitter toward the receiver. And so when the signal is highly localized, it has a very well-defined direction. Maybe unlike some of the diffuse multipath channels that you may have studied in your wireless communication course previous semester, where the received signal really does not have any well-defined direction. Let's say if you are in the middle of downtown Mumbai, there are tall buildings, very congested area. The transmitter, the base station can be somewhere not directly visible to your phone. And the signal coming from the base station toward your phone is not coming in a very specific direction. It is getting bounced off of multiple reflectors, which are maybe the buildings and so on. And so in those scenarios, maybe it is not, it may be not appropriate to talk about a specific direction of arrival of our received signal. But in the millimeter wave next generation systems, a lot of the channel models are what are known as this specular models, where in many of these papers, the matrix formulation or the algebraic formulation is very this uniform linear array channel model that we have seen. And so in that context, the DOA problem is also highly pertinent. And we have seen multiple algorithms that solve the DOA/FOA problem. I think you studied these algorithms as part of your currently ongoing lab. And then over past maybe almost 3 to 4 weeks, we have kind of shifted our focus a little bit, and we have said that, okay, suppose if I know frequencies, if I know the directions, so that I can actually determine the array vector or the temporal signature vector, and I can collect all of those vectors for different transmitters in a matrix. And then now my goal is not obviously to do DOA or FO estimation, because I'm assuming that those I have already estimated. My problem is now, given the knowledge of DOA, I want to know what are the transmitted symbols. And that becomes essentially the demodulation problem. Except we have called it a generalized demodulation problem because there are multiple transmitters that may not be co-located. And their corresponding vectors, their signature vectors, may not be orthogonal. And so then we have to consider what are the possible techniques that we can use to solve the problem. Okay, so with that as kind of a high-level recap, let us continue on the topic that we had started out on, with last time. Okay. We looked at this generalized demodulation problem in the context of beamforming. And then we saw that the code division multiple access signal model is also very much like that beamforming problem. MIMO signal demodulation also conforms to the same linear algebraic model, as well as the problem of deconvolution can be cast in the same framework. There's one more problem statement which I have still not included here. Hopefully I will do it next time, which is the problem of channel estimation for, let us say, OFDM or for MIMO, etc. And that also can be cast into this unified problem statement that we had seen last time. And in the context of this unified problem, we saw there are 3 different solutions that we can use. Who can tell me what these 3 solutions are?
SUMF decorrelator and MMSC.
Yeah. The single user match filter, the decorrelator, and the MMSE. Now, there is one aspect which is common to all of these 3 solutions, which is what is a common mathematical characteristic of all of these 3 methods?
Projection.
So they have a linear model.
Sorry, Joel, can you repeat?
So linear model. They all have.
Yes. So all these 3 techniques fall into a class of techniques which are called linear schemes. Basically, other than matrix multiplies or possibly inverting a matrix and then multiplying it with a vector, we are not doing anything else. Sometimes we are just not even inverting the matrix. For example, single user match filter does not require a matrix inverse. So these 3 techniques belong to the class of techniques which are known as linear methods. Now, it turns out that these linear methods are not the optimal methods when this basis functions or the basis vectors are not orthonormal. If they are orthonormal, then the SUMF gives you the right answer. you don't need any other method other than the single user match filtering. And that is what we saw in CT516. But because of the non-linearity, we cannot say that, because of the non-orthogonality between the basis vectors, we cannot say that these linear methods remain the optimal. Actually, the optimal scheme, which is the maximum likelihood scheme, requires the exhaustive search over this multidimensional space. So what I mean by that is that if you recall, in CT516, we had seen that this maximum likelihood scheme or the maximum a posteriori scheme, they boil down to distance minimization scheme. And specifically, we consider our received signal vector as occupying one point in this multidimensional space, which is occupied by all of the possible transmitted symbol vectors. And we want to select that particular transmitted symbol whose Euclidean distance is the smallest relative to the received vector. So if we can actually do that minimization of distance in the Euclidean geometry, then the answer that we get will be optimal. The performance that we will get is going to be the superior performance. It cannot be improved upon. The problem with the distance minimization approach is that if we do it in the brute force manner, in an exhaustive manner, then it can become computationally intractable. We may not be able to solve the problem at all on an FPGA, for example. So I'll give you one example that let us say that we are considering a MIMO system with, let us say, 256 antennas. And we'll say that on each antenna, we are transmitting a QPSK symbol. And this is a spatial multiplexing MIMO, SMUX MIMO. And so, as we had seen in one of the earlier lectures, each of the transmit antenna is active simultaneously, and it can independently transmit one of 4 symbols of QPSK constellation. Okay. Now, my question to you is that if I want to do this optimal reception, which is the Euclidean distance minimization, after receiving a particular signal at the receiver array, how many points in the Euclidean geometry, in the Euclidean space, multidimensional space, will I have to compare the received vector with? Meaning that how many distance values will I have to compute before I can minimize the distance?
So can you repeat the start part of the question?
My question is that if I am considering a transmit antenna with a MIMO system with an array of transmit antennas where there are 256 antenna elements in the transmit array, my question is how many points, how many possible constellation points there are. Remember, for a very simple MIMO system with only 2 transmit antennas, we considered the constellation diagram when each antenna is transmitting a QPSK signal. Who remembers how many symbols did that constellation diagram have?
4.
We had seen the constellation diagram for an S-MUX MIMO, where there were 2 transmit antennas, some arbitrary number of receive antennas, and we drew the generalized constellation diagram for this S-MUX MIMO. And I want to ask you, first of all, how many dimensions that constellation diagram have, and how many points, how many symbol values were there in that constellation diagram?
Sir, dimensions were 2.
Uh-huh.
And sir, number of symbol points was depending upon how many active antennas there
No, I'm
were.
saying both. This is a spatial multiplexing MIMO, so both the antennas are active simultaneously.
65.
Uh,
8.
8.
no,
Okay, on constellation 4.
each antenna is transmitting QPSK.
Yeah. 3 at
We had exactly the same question some time ago, and I think,
Kishan answered.
yeah, so
So like
So
16.
16.
16,
Yeah,
right?
16.
16, right? Each antenna is transmitting 4 QPSK symbol independent of what the other antenna is transmitting. So there will be 4 times 4, 16 points in the constellation diagram. And the way we drew that constellation diagram seemed a lot like as if it was a 16-poem constellation. Now, given that, I think you should be able to answer this question I have, that if instead of just 2 transmit antennas in the 5G systems, where there are design plans to deploy maybe as many as like more than 200, 300 antennas. So let us pick up a number. Let's say that there are 200 antennas at the transmit array. And let us again say that each antenna can independently transmit one of 4 QPSK symbols. Then what will be the dimensionality of the constellation diagrams, that constellation diagram, and how many points will that diagram have?
So going by the logic, dimensionality will be decided by the modulation scheme. Like if QPSK, then 2. And
No.
Sir, is it 8 dimensions?
the number of points will be 4 to the power. The number of antennas.
Remember, where are the new dimensions coming from in the MIMO system?
The number of
The spatial, that's why it
spatial
is
constructs.
dependent on number of antennas.
Number of antennas, yes.
Yes.
Basically, each antenna corresponds to a unique column vector of that MIMO matrix, H matrix. Remember that H matrix in MIMO has dimension of NR plus NT. And potentially each of the transmit antennas can give you a new dimension. And so if I have NT antennas, NT different antennas, I can potentially have NT different dimensions. That is why in that example with 2 transmit antennas, I had 2 dimensions. First dimension was antenna 1, the other dimension was coming from antenna 2. So now if I have 200 antennas, the dimensionality will become 200. And on each dimension, I am free to independently transmit one of 4 values. So in the entire multidimensional space, how many points will there be?
200 raised to 4.
the power 200.
Correct. 4 to the power 200. Now, 4 to the power 200 is a big number. It's a humongous number, actually. I don't know exactly, but it probably is bigger than the age of the universe in the seconds. It's a humongous number. And now every time I receive a particular symbol vector out of this 200 dimension space, and if I want to compute its Euclidean distance to all of these 4 to the power 200 points, then forget about it. It is going to be computationally impossible thing to do, but also it will be just from the point of memory, it will not be practical approach at all. To store 4 to the power 200 values and then do some type of sorting operation to figure out which one is the smallest is not possible. It's not possible today, and I don't think it is going to be possible ever in the future. So the optimal demodulation for this type of systems, if you talk about either beamforming, Cdma, MIMO, the deconvolution, etc., the optimum technique is known, it is well known, but it becomes computationally intractable. Now, there are some smart solutions which have been invented, and one of such smart solutions actually employs the Viterbi algorithm. I don't know whether we had a chance to study Viterbi algorithm in CT516 or not. I forget whether I was able to cover the convolution coding and Viterbi decoding in that course, but if you're familiar with Viterbi algorithm, in fact, that can be applied to, instead of directly doing the distance minimization by brute force technique, the Viterbi algorithm can be used. But it turns out that even the Viterbi algorithm, which significantly simplifies the computational cost compared to searching over 4 to the power 200 points, it still is impossible. So if you have a problem which allows you to, which requires you to count the age of universe in seconds, instead of that, if you simplify that problem by a factor of 60, and if you are asked to count the age of universe in hours, yes, the problem has become simpler, but it is still impossible. It's too many hours since the birth of the universe. So it is that type of situation. So the Viterbi algorithm-based approach for optimal demodulation also falls short of what is technologically feasible. There is one more algorithm which is known as sphere decoding algorithm, SD, sphere decoding, which actually is almost optimal, and it actually solves the problem in a reasonable manner in terms of computational and memory requirement. But it is not a linear algorithm. What it does is, after observing a received signal vector in this multidimensional space. So think of this multidimensional space as you know, our familiar 3D space. And let us say that I have observed a particular, let us say, a ball or something, a balloon or something, kind of at a particular location in this 3D space, and I have many other balls which are these constellation points. And now I just want to figure out which of the constellation point is closest to my received signal vector, the particular sphere, the particular location that I have observed. So what this sphere decoding does is it says that I will create a small sphere whose center is my received vector, and that small sphere I will make it to have, first of all, a very small radius. And now I will see if there are any point out of this 4 to the power 200 constellation points, if there is any point that falls within this sphere centered at my received vector location. If there is a point like that, and if it is only one unique point, then I'm done, because that has to be the closest point to my received vector. If there is no such point, if I don't have any point within this sphere that I have created, then it means that the radius of the sphere is too small. I need to enlarge the radius. So I will enlarge the radius, and then I will again determine if there are any points which fall inside the sphere. Maybe now I have enlarged the radius and more number of points have, so some points have fallen inside the radius, but the number of constellation points that are inside that sphere of that specific radius hopefully will be much, much, much smaller than this 4 to the power 200. And so now I will have to just solve the distance minimization over only those constellation points which are inside the sphere of this particular radius. So that is known, that is in a very high level concept is the sphere decoding algorithm. The problem with SD, the sphere decoding, is, first of all, how do you determine the radius? If you make it too small, then none of the constellation points will lie within it. If you make it too large, and instead of, let us say, 4 to the power 200, even if 2 to the power 50 points lie within the sphere, then 2 to the power 50 is still a very big number. You can't solve that problem. And so that is one problem, how to determine the size of the sphere. The second problem is, how do you know which points lie within the sphere? If you have to go to each and every of this 4 to the power 200 points and individually determine whether it lies within the sphere or not, then we are back to square one, right? I mean, we can't do that type of calculation individually for all the points. So the sphere decoding is a smart technique which solves both these problems. And it has gained a lot of attention. Maybe we will go over the detailed concept of sphere decoding in a subsequent lecture. But the reason I want to bring that here today is that these three techniques that we have so far studied are much, much simpler techniques. They are confined to the linear algebraic method. They don't do this exhaustive search, or they don't do Viterbi algorithm, etc. And so therefore the performance definitely is not the best possible performance that you can get. Is there some intermediate way? On one side, we have this linear techniques, the SUMF, the decorrelator, the MMSE. On the other extreme, I have the brute force search, which is impossible, or the Viterbi algorithm, which is also impossible, or the sphere decoding, which is tractable. So those are the other possibilities. Are there any other intermediate ways which actually give us better performance compared to the linear techniques, but they are not as computationally intensive as some of these brute force methods? So that is the topic of today. We are going to be studying the non-linear methods of performing this generalized demodulation. Okay, so that is the topic for today. We already did the analysis part last time. So I'm going to skip over that, and I'm directly going to go to this non-linear techniques. The first non-linear technique that we will be looking at is called successive interference cancellation. Now, you may feel that, okay, we are moving forward from the linear techniques, which we have understood in a clear manner mathematically. This requires just the correlation matrix and maybe taking the inverse of correlation matrix, etc. You may feel that compared to this linear techniques, which we have kind of become familiar with, this non-linear techniques may be complicated algorithmically and also maybe conceptually. The word nonlinear in general is not viewed favorably in the research community. If you have to perform performance analysis, then linear techniques are amenable. They can be solved. You can analyze the performance of linear techniques, at least to some extent, like the way we did last time for SUMF and for the decorrelation. When we enter the nonlinear region, then all bets are off. The analysis of nonlinear techniques is highly cumbersome and may not even be possible. The neural network, for example, is a nonlinear technique. And although currently these days there are many papers written on neural network application of deep learning to solving the communication problems, there is one common theme across all the papers is that the performance analysis part is almost never attempted. That is true in general, even if you are in, for example, computer vision or if you are doing speech processing. A lot of the times, the performance of the DNN or the reinforcement learning is presented only by simulation. Analysis, mathematical analysis is not provided because it is nearly impossible to analyze the schemes in detail. Maybe some simplified cases are possible, but not a thorough, rigorous analysis. So yes, indeed, the techniques that we are going to be looking at are highly complicated to analyze in terms of their performance. But I want to emphasize and I want to stress that the main idea is actually surprisingly simple. Actually, the concept behind these techniques is actually even more easier to understand than, for example, decorrelation or MMS. In fact, you might almost feel that this is like your 9th grade or 10th grade math. Well, you might feel that it's trivial, in fact. The concept is very easy to understand of these techniques. But because there is non-linearity involved, we may not be able to fully understand how these techniques perform when there is all this interference present and noise is present. So with that, let us start with successive interference cancellation. And I'm going to consider only first just a case when there are two users. And so you may recall that for the two-user case, we have modeled the output of the SUMF like this. Z1 is the output of the single user mesh filter for user 1. It has the desired component A1, B1, it has the noise, which is U1. But then there is this interference, A2, B2 times rho. And last week when we analyzed the single user match filter, we saw that the performance of this SUMF to a large extent is determined by the value of A2. And specifically, we considered something called near-far effect. Do you recall what that near-far effect is?
Yes, the example, if a user is located very close to the tower, one is very far. So
Yes.
for the far person, the user who is near the tower, that particular user itself is going to act as a interference for the user at the far end, other than the noise, more than the noise itself in the channel.
Right. And it can so happen that even in a hypothetical case, the noise is not present. The far away user may see 50% error. If A2 times rho is bigger than A1, then whenever B1 and B2 are same, this user 1 will get correct output. Otherwise, the user 1 result will be wrong. And the probability that B1 and B2 are same is 50%. So half of the times user 1, even in the absence of noise, is going to see errors, which is clearly unacceptable. So that is the drawback of the SUMF. And so we see that SUMF falls short, especially in this near-far scenario. Now, there are Cdma receivers. Actually, some of these Cdma techniques are still present, which purely because of computational simplicity, they use the SUMF. They do not do the decorrelation, they do not do the MMSE. So because of ensuring that the receivers of this CDMA systems remain computationally simple, the SUMF is adopted as the implementation scheme. But the designers of such systems obviously knew about this problem, the near-far problem. And so in many such CDMA systems, there is a requirement from the system design point of view to implement what is known as power control. And so what the power control is that the base station, the tower, will monitor the received amplitudes from different users. It may not know the position of different users, but it will know the levels, the power levels at which different users are being received. This near-far effect happens because there is one user which is being received at a much, much higher power compared to the other user. So there is an elaborate mechanism which is known as power control, which is implemented in the CDMA systems, in which the base station tells the nearer user to dial down its power. And so that the nearer user attenuates its signal. And so even although it is closer to the base station, A2 becomes almost same as A1. Basically, the objective of power control is to make sure that all of the users within the cell, within the coverage area of this base station, are received at the same power level at which the weakest user is being received. Okay, and if you know about a CDMA system called IS-95, which is one of the 2G systems, IS-95 is considered at the same level as GSM. But in the 1990s and even in the early 2000s, IS-95 based systems were everywhere. Not in India, but in USA, in South Korea, even parts of China, used IS-95. And so this power control is an integral component of IS-95. Now you can see the problem with the power control. It's like the user whose signal is being received strongly is also asked to attenuate its transmit power. And so that user will not be able to get the type of data rates through as it otherwise would have. It is like if there are two people who are running a 5-kilometer race and one person is very fast and the other person is maybe not physically as fit, and so he runs very slow. Now, the organizers of the race say that, to the fast person, that if you reach the finish line 5 minutes or 10 minutes earlier than the slow person, then that slow person is going to be highly disadvantaged. That person is going to be unhappy, and so we are asking you to run at the speed of the slow person. And so obviously the person who is physically fit is not going to be happy. It is not a fair outcome for that person. So that is the problem with the power control, and specifically the problem with the SUMF based schemes for CDMA systems. Now, I don't want to minimize the application of power control in CDMA systems. I think there have been far too many research papers written, and there are many, not only MTech, but even PhD dissertations written on this particular bullet, the second to the last bullet of how to make sure that it works properly so that all of the users are received at this roughly the same power level. That's a difficult problem, and that has been solved in a very sophisticated manner. So that entire body of work, which took place in late 1990s and early 2000, is relevant for many computationally simpler implementations of CDMA. The successive interference cancellation technique that we are now going to look at specifically says that don't do power control. It takes exactly the opposite approach. And it says that if the power control is not implemented and if this situation is present, A2 is much greater than A1, then it is good for me. That is the idea behind successive interference cancellation. And so let us see what that idea is. Because A2 is much greater than A1, A2 is definitely going to be much greater than rho times A1, because rho is less than 1, the correlation coefficient. And so the successive interference cancellation says that I will first decode user 2's signal. And there I will just use the SUMF. In the second line here, if I say that A1 times rho is much less than A2, then I can almost ignore this A1 B1 times rho term. And so I will take Z2 to be almost same as A2, B2 plus U2, which is the ideal case, remember. If the interference is not present, then SUMF gives me the ideal solution. And so that is the main idea behind successive interference cancellation. It will start with the user which is being received the strongest. And therefore, it is quite likely that we will be able to demodulate that user signal correctly. If you are able to demodulate correctly, then we can go to user 1 and we can remove the corresponding interference component which was hurting us in the near-far problem. So if we have demodulated B2 and we assume that somehow we know the estimate of A2, then I can compute A2 times B2 times rho, or A2 hat B2 hat times rho. Once I do that, I'll go to Z1 and just subtract it out. And now I will form the estimate of B1 using that Z1 prime. So if indeed B2 hat is same as B2, which is likely because remember the SUMF for user 2 is nearly the optimal scheme because of this condition. And if you recall in CT516, even if SNR values were not that high, maybe 6 dB, maybe 7, 8 dB, then the probability that B2 hat is not same as B2 was turning out to be pretty small, maybe less than 0.1%. So most of the times, this condition is going to be met in this case. Let us also assume that the estimate of A2 is also pretty good. Then Z1 prime is now also interference free. And so you see, we get the best of both the worlds. We were able to get user 2 demodulated as if there was no interference, which is because of our assumption. And then after that, when we went to cancelling the interference from user 1, we were able to do it almost ideally. So that is the main idea behind successive interference cancellation. This strategy may not work if this condition is not present. If there are two users which are both at the same distance from the base station, then we may not be able to assume that Z2 over here is free of interference from the user 1. So unlike these CDMA systems which employ power control and which actually make the situation unfair for the strong user, the SIC actually takes the opposite approach and says that I will not make the situation unfair for the strong user, and at the same time, I will not hurt the weak user. Both the users will get the best performance that they would have got, as if the other user is not even present. So now let us visualize this SIC scheme by some diagram, because we have so far considered only two user scheme. We'll go on to considering more number of users. Okay, so we'll draw some diagrams of this SIC. But before we do that, let us take a quick break. and then come back to this. Okay, so I'm going to start drawing some diagrams, but yes, Divya?
So this method is quite similar to the Gram-Smith method, right? Where we used to first select a basis vector which is maximally aligned with one of the point which we are dealing with, then removing the correlation with the other.
Yeah, well, it kind of is similar to that. You're right, but the crucial part in which it differs from the Gram-Schmidt method is that it is driven by this B2 hat and A2 hat. And unlike Gram-Schmidt, which we did kind of in an offline manner, even in absence of any transmissions or reception, we, while designing the modulation and demodulation, we use Gram-Schmidt method to determine the orthonormal basis given a particular set of modulation waveforms. Here, this is a real-time scheme. As the symbols are coming in the real time, we are determining the symbols, and then we are subtracting those symbols from, we start determining the symbols of the strong users, and because those strongly received users are going to create much more interference to the weaker users, we will be subtracting their contribution from the weaker users. And the weaker users, their interference is not going to be subtracted out from the stronger user because anyhow, they are weak. They don't contribute that much interference to the strong users. So it may seem a little bit similar to Gram-Schmidt, but the idea is very different actually. I mean, here we are not trying to orthogonalize a set of basis vectors. We are not even, I don't think that in the SIC there is a focus on the multidimensional space and how these different vectors are aligned, whether they're, so first they are not orthogonal and then after performing SIC they become orthogonal. I think that type of viewpoint is not even present here, which is the viewpoint present in the Gram-Schmidt method. Here it's like very down to the earth, very practical, very pragmatist, I would say, solution to the interference removal. I wouldn't, I mean, maybe I'm putting it starkly. The researchers who came up with this successive interference cancellation technique, they must have been mathematically very capable fellows. And I mean, nothing to cast doubt on any of that. But fundamentally, I would say that to come up with SIC, you don't even need to know linear algebra. But what you need to be is street smart. You just look at the problem and you say that, okay, if there is one strong user, there is one weak user, then obviously the weak user is not going to be causing too much interference to the strong user. So I'll just assume that strong user is interference free. And therefore, if I can demodulate the strong user as if there is no interference, then why can't I just remove the contribution from that strong user from from the signal coming in at the weaker user receiver. So it's almost a practically oriented approach. Okay, so now I will look at some diagrams. Now, in order for me to draw these diagrams in a visually unclustered manner, I have made use of some shorthand notations. And so those notations are mentioned over here. Remember, in this SIC scheme, there are pretty much two main operations. One is the sign operation, because we are assuming BPSK symbols. So they can be demodulated by just a sign. Actually, I will have to take a break one more time. Please pardon me. I think my laptop battery is running out. So I'll be back just in a moment. Okay. So while drawing this schematic diagram for SIC, we will need two main visual representations for two main operations. One is the sign function, and the other is this part where we are estimating the interference caused by a stronger user, and then we are removing it from a weaker user. And so this A2 hat, B2 hat times rho is the other part that we will have to somehow draw in a diagrammatic manner. And so that is what I have tried to do over here. The sign part, a lot of the times it is represented like this. When x is greater than 0, y is equal to 1, x is less than 0, y is equal to minus 1. The interference cancellation part is this operation. There is some node j, and this node j, is going to be our bit estimates. B1 hat, B2 hat, B3 hat, etc. And the node K is going to be our SUMF output. This is going to be Z1, Z2, Z3, etc. And the bit estimate formed by a strong user is going to get multiplied by this quantities. And that is going to be sent to the SUMF for the weaker user, so that the interference from this strong user can be removed at the output of the SUMF of this weaker user. J is the strong user, K is the weaker user. And that exact removal is happening by this little tiny dot here. And that is going to be represented by this operation. X, and this Y will have minus sign. So what we are going to get is summation. So these three different operations, in order to simplify, I will be representing it by colored arrows. So wherever you see the red colored arrow, you have to say that the input is going to get converted to the sign only. So red is this BPSK demodulator. Basically, it takes the sign of the input. So Y is the sign of X. The green arrow means you are taking a bit estimate, which is either 1 or minus 1, and then you are converting it to minus AJ hat, BJ hat, and this correlation coefficient. And then this is finally just the summation. Is this clear?
Yes, sir.
Okay. So let us now represent this SUMF algorithm. Step 1, 2, and 3. Let us represent them diagrammatically. So this is the step 1. This is SUMF for user 1. This is SUMF output for user 2. And in step 1, user 2, remember user 2 is the stronger user. So we just do the BPSK demodulation. This red, remember, is the sign operation. So we just did the BPSK demod. We took the sign of Z2 and we got B2 hat. Remember, this B2 hat is going to be now our driver of the interference cancellation. So we are going to multiply B2 hat with negative A2 hat times rho. And that operation is this green arrow. And that is going to go to node 1, the weaker user. And so that is this operation. And then finally, node 1 will take the weaker user SUMF, will get added by this negative A2 hat, B2 hat row. And then we just take the sign operation on that, which is this red colored arrow. So this is a way to diagrammatically represent the SUMF algorithm. Is this clear?
Yes, sir.
Yes, sir.
So now, once you are clear about what this red and green arrows represent and what these circles and squares represent, it's clear how to extend it to 3 users case. Can you tell me what the 3 user case will look like?
We'll
So
first pick
from
the
B1, another green arrow will go to another symbol, and then it will be decoded after
Correct.
subtracting its interference component.
Correct. So first of all, there will be 3 squares because there are 3 different users. So there will be 3 different SUMF. There will be 3 circles because we have to demodulate for the 3 users separately. But if we are ordering the users, and from now on, the users are always going to be ordered such that user 1 is the weakest user, user 2 is going to be the next stronger user, user 3 is going to be next the strongest user, and so on. So for the 3 user case, oh, okay, so before we go to 3 user case, let me make some few remarks. Okay, first of all, this technique is non-linear because the sign operation is not linear. You cannot implement the sign function by any linear technique. Okay, so that is why it's a non-linear technique. And if the probability that the estimate B2 for the stronger user is in error, if that error probability is small, then there is a good chance that it will work better than the earlier techniques. What do you think are some other requirements? Yes, Bhavesh?
Sir, can you repeat that part when you said that the non-linearity is because of sign? It is a +1 or a -1, right? We are creating a BPS.
Yeah. What I'm saying is that when the function looks like this, you can't implement it using a linear method. The linear methods look like a straight line.
Okay, okay.
Here there
Like
is
y is equal to mx plus c, we cannot represent them like that.
exactly.
Definitely.
So that is why this SIC becomes nonlinear. Now, what is the other requirement that has to be met so that this SIC works well? We already talked about it over here. So one requirement is that the probability of error for the stronger user should be small. What is the other requirement?
The rho should be very, very less compared to 1. The
No,
correlation coefficient.
the correlation coefficient can be any value between -1 to 1 because we are removing it out. Remember, here, even if rho is big, the contribution is getting cancelled. So we do not require rho to be small. Actually, that is one of the benefits of SIC. But what is the other requirement? Arushi, what do you think?
Sir, there should be much. There shouldn't be all the users shouldn't be at around the same user level. They should have a power difference.
Yes, Joel, that is correct. We said that. In fact, SIC leverages upon this near-far effect. So if the near-far effect is not present, then it can be a problem because it is not clear that we can eliminate, we can assume that user 1 is not contributing any interference to user 2 when both the users are received at nearly the same level. So that is definitely a very important requirement. Anything else? Well, other requirement is that we should have estimated A2, right? We haven't talked about how A2 is getting estimated. So that is a separate problem. But we have to have that A2 estimated, and that estimate better be accurate. Because if that estimate is itself inaccurate, then when we go to cancel user 2's interference from user 1, that cancellation will not be precise. The third is the point that Joel mentioned, that we want the power imbalances. Power is proportional to square of the amplitude. And so equivalently, we want the amplitude levels to be highly different. If all the users are at the same level, then maybe the SIC is not the best thing to do. And then finally, we want our algorithm to demodulate user 2 first. And then we want to demodulate user 1. This is just the algorithmic part of it. I mean, nobody would miss this, but it's important to note that this is a requirement. What happens if, suppose, someone who is kind of not as much familiar with SIC says that, no, I will decode user 1 first, and then I will demodulate user 2, meaning that instead of doing it like this, the arrows are exactly reversed. What will happen in that case?
So we will not be
Error
able to decode
amplification.
user 1 correctly because there will be a lot of interference components from the user 2 in present in user 1 while reception.
Yeah. So maybe user 2 will still turn out to be okay because that user is the strong user, but user 1 will be wiped out more or less because of that near far effect. And secondly, if that near far effect is not very pronounced, actually, because user 1 is going to most likely, I mean, not most likely, but with a high probability nearing maybe 0.5, is going to be demodulated wrongly, it can actually exacerbate the interference present in user 2. You might end up doubling the interference. See, over here, this Z1 minus A2 hat B2 hat rho, if the sign of B2 hat is same as B2, meaning B2 hat is same as B2, then yes, from Z1 you remove this term. But if B2 is estimated wrongly, then what happens is instead of making this term 0, you double it. Does it make sense?
Yes, sir.
So in the good case, the SIC removes the interference. But in the bad case, when B2 is estimated wrongly, actually it hurts the performance. It's better to not even do this. And so in case if you mess up the ordering in which you cancel the interferers, it is likely that the SIC will work worse than SUMF. So these are some of the caveats that we have to understand about the SIC. Okay, so now we can draw the diagram for the 3 users case. So we take the strongest user, user 3. We just apply the sine function to get the BPSK demodulated symbol B3 hat. Now that B3 hat is sent to both user 2 and user 1. And this green arrow is not just B3 hat, remember, it is B3 hat, A3 hat, and row between 2 and 3. And then you also put a minus sign. And so what comes to this gray circle is this quantity, which is what we are removing. And the output of the gray circle will be the SUMF plus this term, the interference cancellation term. So B3 hat is getting cancelled out both at user 1 and user 2. And then B2 hat is getting cancelled out only at user 1. So now that we know the 3 users case, obviously 4 user case looks very similar. The reason I drew these diagrams in this manner is because pretty soon we will be looking at the message passing algorithms as they are applied to, for example, LDPC codes. And there we will be actually looking at diagrams which look like this. So to draw the analogy with the message passing algorithm, such diagrams of SIC will be useful. So now that we understand the basic concept of SIC, we can formulate the general case. So what we do is first we somehow estimate the amplitudes. After estimating the amplitudes, we order the users so that always the strongest user is indexed as capital K. The next strongest user is K minus 1 all the way to the first A1. Then we demodulate the strongest user by just using its SUMF. We don't do any interference cancellation. We assume that for the strongest user, the interference from all the weak users is negligible. Then we go to the next strongest user, but that time we remove the interference at this user K minus 1 coming from user K, which we have already demodulated. So this is the operation we do. Then we go to the next user, but now the next strongest user, we remove the interference from user K as well as user K minus 1. And so that way we keep on decrementing the user index. When we are at some arbitrary index small k, which is between capital K and 1, we demodulate that user by taking its SUMF and removing the interference from all the users that are stronger compared to user K, which means user number K plus 1 all the way to K, capital K. So that is the algorithm that we know as SIC, and this is the general block diagram for that. So I think after this exam next week, we will start on another lab/project in which you will be implementing the 3 linear methods as well as this non-linear methods. And I think algorithm should hopefully be clear enough to you now that you can implement it in MATLAB. Now, one thing to note here is that as we go from the right to the left, the densities of arrows coming at this gray circle starts increasing. But the density of the green arrows leaving the symbol estimate circles starts decreasing. This circle is connected to all of the SUMFs except itself. Whereas this circle is connected to only one SUMF. This circle is not connected to any SUMF. In same way over here, we see that the cancellation is happening maximally for the user 1, which is the weakest user. And the cancellation is not happening at all for the strongest user. So in a general case, we may not be able to say that this kth user is very, very strong compared to K minus 1. And K minus 1 is very strong compared to the next user, K minus 2. And so it may not be it may not be possible for us to say that we have entirely cancelled the interference from all the users. Okay, so that motivates the next algorithm that we are going to look at now. And this algorithm is called parallel interference cancellation, or PIC. And it is also an iterative algorithm. SIC is not an iterative algorithm. You do this process one time and you are done. Whereas PIC, you can keep on repeating. Any guess as to what PIC may look like in terms of this diagram?
So grouping the users which are at same power level.
No. That is done. Your point is valid. But in terms of the interference cancellation algorithm, that is not what is meant by the parallel implementation of IC.
Instead of removing the interference like user by user, it is simultaneous maybe.
Yes, to some extent, I think what you're saying is correct. But look at this diagram. How would you modify this diagram if you had complete design freedom to do so?
So all of these circles and boxes will be connected in that, but
Yes.
they will be assigned different weights as per like how strong is the reception.
Yeah, no, so that is not even done. But the first part that you said is correct.
Okay.
This is called partially connected network. We can think of PIC as a network which is fully connected. So let us first of all look at how it looks like mathematically, and then we will draw the diagram. Remember, PIC can be done in an iterative manner, so that the iterations are called stages. So this algorithm is also known as multi-stage algorithm. So in the user, when capital K is equal to 2, the first iteration of algorithm just estimates the symbols of the two users using standard BPSK demodulator applied to SUMF. And this superscript denotes the iteration index or the stage index. Now remember that in SIC, we just make use of B2 hat to cancel the interference from Z1. And that makes sense if there is a great disparity in the power level. But as we just now mentioned, when there are total of capital K users, where K can be like 20, 30, like that, we may not be able to say that there is a great disparity between the power level of user 30 and user 29. And so what the PIC says is that I'm going to do SIC on both the users. I will take, just like SIC, I will take user 2 estimate and remove it from the SUMF of user 1. But also I will take the estimate of user 1 and remove it from user 2. Now, just now we said that if it is only a 2-user case and if A2 is much greater than A1, then actually this second step is not really the right thing to do. Because it's quite likely that B1 hat is going to be wrong in this first iteration. And so when you think that you're removing the interference, but maybe not. Maybe you are actually doubling the interference. So when the power levels are highly different, then this doesn't make too much sense. But in the real world, sometimes you get power levels which are not that much different. Well, in that case, maybe this is not too bad. That is the main difference of PIC compared to SIC. And the other difference is that PIC says that why do I stop here? I will repeat it one more time and then one more time and so on. Basically, I will keep on iterating, and at ith iteration in this equation, I will replace B2(1) with B2I minus 1, the estimate that I got at the previous iteration. So that is the main idea behind PIC. You can think of it as a kind of an extension of SIC with iterations. Now we will notice that user ordering is not needed here at all. You still need to estimate the A values, but whether you estimated them accurately enough so that the users are ordered in the right manner, it becomes irrelevant here. And this is how the diagram looks like for PIC for the case of 4 users. I want to draw one more diagram which illustrates the iterative aspect of the PIC. Oh, okay. Before I do that, this is one question for you. How would you write the symbol decisions? This B1 hat, B2 hat, B3 hat, B4 hat. Let us consider them as forming a 4x1 vector. How would you write that vector? Any idea? Okay, so who has not spoken? Arushi, are you there?
Sir.
Okay. Do you have an answer to this question?
Sir, I did not actually understand.
And I'm asking for this scheme that is
Yes.
shown automatically here, and maybe I already gave you the answer. It is shown by equations here. How would you write the vector as equation? Anyhow, I'll just give you the answer. See, whenever you see this fully connected network, you have to start thinking of it as diagrammatic representation of a matrix. In this case, this matrix is nothing but the matrix R of correlation coefficients. We multiply R by A. Sorry, this should have been A hat. This is a typo error. Multiply R by A hat. And then this B hat is just the vector of the symbol estimates that we have formed prior to the in the previous iteration. So this would be one way to represent this equation. Except I would say that there is one part which is not captured here, which is that there is no arrow going from B1 to Z1 and similarly B2 to Z2 and so on. And so I think this notation R also has to be modified. The diagonal terms of this R are all zeros, because we are not feeding a particular bit estimate to itself in the next iteration. So diagonal terms are all zeros. Other elements of the correlation coefficient, correlation matrix remain the same. So I will leave this equation with you and think about it, whether this makes sense. So now I will actually do the last thing about on this PIC topic, which is to draw the iterative version of the diagram, which is shown like this. So we have the SUMF. In the first iteration, we just do the sign operation on the SUMF output, and we get the SUMF bit estimates. Now we do the parallel cancellation, which is drawn by this green arrows. And that cancellation is also happening on the SUMF output. So we bring the SUMF output to our next stage. And then we do this red arrow, which is, remember, this is just the sign operation again. So this is our stage 2 output. And then we again repeat the same process to get stage 3, and then again repeat it to get stage 4, and so on. So this is the idea behind the multi-stage interference cancellation. The last algorithm that we will discuss today in maybe another next 10 minutes, it is called decision feedback algorithm. And first of all, let us motivate the decision feedback algorithm by recalling that the SIC doesn't remove the interference from the weaker users. So interference cancellation is not complete. PIC removes the interference from all the users, but unlike SIC, it might end up wrongly compensating for the interference, especially when it tries to remove the interference of a weak user from the strong user. And there is a chance that weak users' output is highly interference prone. Then maybe that is not the right thing to do. So the next algorithm that we will be calling decision feedback algorithm, it will solve this problem that SIC had, which PIC tried to solve, but kind of it solved the problem a little bit imperfectly. Basically, in solving the problem of partial interference cancellation that SIC had, the approach that PIC took could end up boomeranging and hurting itself. So this next algorithm, this decision feedback algorithm, is a more perfect solution to this SIC problem. And now here we bring the linear algebra back. Remember the Cholesky's factorization that we did last time? So we'll be making use of that. This algorithm is called decision feedback, maybe because the researchers kind of ran out of the words, the nomenclature. Because in fact, if you think about it, even the SIC and PIC are also decision feedback. We are making the decisions and then we are feeding them back. So that way, the next algorithm is no different from SIC or PIC. The main difference is that this Cholesky's factorization is leveraged. Who remembers last time that if we can factorize this correlation matrix R using this Kolesk's method, then we can actually do the noise whitening. Do you remember this topic we discussed last time?
Yes, sir.
Okay. Komal, how about you?
Hello.
Yes. Do you recall this topic, Komal, that we did last time?
Yes, sir. We tried to color because noise was that time colored, so we tried to make our noise whitening of the noise. We were trying to do.
Correct. The way we did that whitening of the noise was we took the SGMF output and we multiplied it by the inverse of F Hermitian. And remember, R is written as F Hermitian F. And so if I multiply Z with F Hermitian inverse, I get F times A times B plus U hat. This F coming out of Kolesk's method is a lower triangular matrix. And its diagonal elements are all going to be non-negative. That is other requirement for this decision feedback scheme. So let us take an example of, again, a 4-user case. And so, suppose I have done the noise whitening transformation. And now the whitened SUMF output, this vector Z cap, which is equal to FAB plus U cap, is what I'm writing here. F is this lower triangular, A is the diagonal matrix, and this is the algebraic formulation that comes out. So now I can write this in a by using equations. And because of the lower triangular nature of this Z cap, this is how the equations come out. Now, there are two important things. First of all, these U values are all uncorrelated. So noise has been whitened. There is no interdependencies between the noise. So that is one good advantage. But what do you think the other advantages of this representation? Kishan, any idea?
Sir, it is easily solvable.
No, yeah, it is easily solvable. That is correct. But in the context of these limitations of SIC and PIC that we were talking about, remember that is how we motivated this decision feedback scheme. So, do you think something makes sense over there? Bhavesh, you are audible.
Hello.
Yeah.
I was saying that after that manipulation now it has become a completely linear problem to solve.
No.
Sir, if we look into Z1, it has only A1, B1 plus U1. This is a BPSK or any other simple demodulation which we have to do.
Mm-hmm.
So basically, Z1 had the effect of A2, A3, and A4 are not accounted for in this case.
Yeah, I think you're correct, but I would put it more strongly. They are not accounted for is not probably the best way to say it. I would say that they don't need to be accounted for because the effect of second, third, and fourth user is not even present here in the first user.
Yes, sir.
Remember the limitation of SIC that we had observed is that SIC looks like this skewed diagram. It's not a fully connected network, which means that the interference is getting compensated only partially. In fact, if you represent the interference compensation that is happening in the SIC by writing it in a manner like this, what you will observe is that not only I have to zero out the diagonal component of R, but I will have to zero out the lower triangular part of R entirely. That is what I'm doing. When I'm zeroing out, when I don't zero out anything other than the diagonal component of R, I get this fully connected network. Each node is connected to all the other nodes except itself by these green arrows. That is when R, only the diagonal of the R has been zeroed out. And that is why we don't see any green arrow going from one circle to its parent square node. But other than that, all the other values of R are present in the PIC. And so that is where PIC can claim that I am trying to cancel out the interference from all the users. In contrast to SIC, which cancels out interference in this lower triangular manner only. This type of connections represent a triangular matrix whose only lower triangular part is present. The diagonal part and the upper part is not even there. But that obviously leads to this limitation that because we are assuming that R, or not assuming, but we are ignoring the upper triangular part of R in SIC, we cannot say that we have cancelled interference from all the users. Well, here the matrix itself is lower triangular. So now this particular representation of PIC is perfect. We don't need the full connectivity because all the other connections are zeros because of the lower triangular nature. So that is the main idea behind this decision feedback scheme. It is very much similar to SIC, but the two differences are that the correlation coefficients rho are replaced by this F values. Remember, this F is coming from the square root factorization of R, Cholesky's factorization of R. And F is lower triangular. And now this lower triangular nature in general, it can be lower triangular or upper triangular. Basically, the triangular nature of F matrix means that if we just implement SIC, then we will be doing complete interference cancellation. And so the algorithm is, again, that we implement essentially the SIC, but instead of using rho values, we use F values in SIC. And instead of using SUMF, we use the whitened SUMF. So the algorithm looks a lot like SIC. Only notation change that I need to make is in SIC, where this particular variable was rho kj. Now I have to replace it by f kj. All the other notations remain the same, and so I get this particular diagram for decision feedback. So this is the third algorithm that typically performs better than either the SIC or even the multi-stage PIC. Okay, I think I have a notation issue, the typing issue here is called decision feedback cancellation. I have the correct title over here, but then in this slides, I forgot to change the title. Okay, so I think let us stop here. What we will do now, starting from the next lecture, is that we will get into the non-orthogonal multiple access schemes. And there, some of the techniques, the non-linear techniques that we have studied today, they will be highly used. They will be highly leveraged upon when we look at the NOMA techniques for 5G communication. So I'm going to stop here. And